I'm creating a series of videos about bashing geometry with complex numbers. Complex numbers are known to fall into algebra, but complex numbers, surprisingly, help a lot with a lot of geometry problems. And in this series of videos, we'll be showing how to apply them. We'll start from the basics, but we assume that you already know what a complex number is and how to manipulate them, aka add, multiply, divide, etc. So let's get started. We'll start with the unit circle and the complex plane. So the idea of the complex plane is that it looks a lot like a Cartesian plane with two intersecting lines like that and at a right angle. And the idea is every complex number, a plus bi, can be represented by a point on this plane. For example, let's just say that a complex number a is 3 plus 4i. Then the complex number would be here, where this length is 3 and this length is 4. So this would be a. That is where a would go. So that's the complex plane, an introduction. So now what's this unit circle thing doing here? So the unit circle is, let's call the point where the two axes of the imaginary axis is this one, and the real axis is this one. And so the point where these two axes meet is at the point 0. And the unit circle is the circle with center 0, so basically the origin in Cartesian plane with radius 1. So that's the unit circle. So note that any point on this circle, for example, let's just call this point over here A, then we know that the distance from A to 0 is always going to be 1. And what's this distance from A to 0 called? That's called the magnitude of A. And in that case, for any A that lies on the unit circle, the magnitude of A is 1. So that's an introduction. So how does this even help with any geometry problems? So we'll give some unit circle tricks later, probably in the second video. But we'll start with finding some centers of the triangle and how this really works. So let's draw this again. And so normally when you're solving a complex plane problem, you want to draw these axes because when you're solving it, you don't have to deal with the real and imaginary. You just deal with the complex number itself. But we're just drawing this to illustrate a point. So almost every single geometry problem has a triangle. So and it usually Olympiad geometry problems don't give you information about the triangle, or they may just tell you that it's acute or isosceles or something. So what you do is you can translate and scale and rotate and scale the triangle so that its circumcircle is the unit circle. This is always possible. Assuming that the triangle is, this is always possible because all the triangles have a circumcircle. And you can also do this with the cyclic quadrilateral sling. And figuring out which triangle to put here is called the setup of the problem. And usually it's just the main triangle that they give you, if that exists. So let's call this triangle ABC. So this point is, let's just call that complex number A. The idea of complex bash is that we can find the complex number corresponding to every point that we're trying to find. For example, So let's just say we have a triangle ABC, and what's the complex number corresponding to the circumcenter of that triangle? Well, this is already given to us because we assume that the circumcircle is the unit circle, and so the circumcenter is going to be 0. So O. So now let's try finding the orthocenter. This is harder to find, and I don't really want to go through and finding it, even though there's like a lot of different elegant ways, because we want to go through these so that we can start actually applying complex numbers. But you should definitely try to prove this on your own. H is A plus B plus C, and which is the orthocenter, and G is A plus B plus C over 3. I is harder to find, and we might find it in a later video, but here are the main 3 center triangles, centers of a triangle. Okay, so let's start talking about variables to define. So questions have something called degrees of freedom, which is basically the number of variables you need to define to determine the entire figure. So for example, for an arbitrary triangle, an arbitrary triangle problem has 3 degrees of freedom because for example, it's determined by its side length. So the number of variables we need to find is the number of the number of variables we need to define is the number of degrees of freedom. So a triangle has 3 degrees of freedom. So for a triangle, we define A, C, and B, A, B, and C for that triangle. So that determines the number of variables we need to define. Sometimes you might define more variables than degrees of freedom so that you can have some extra room for symmetry and stuff, but normally you define the same amount. Okay, so let's get started with some simple formulas. And then we might go with an easy example. Okay, so let's see. So let's look at some formulas that you absolutely need to know, among others that we'll discuss later. So let's bring up a complex plane again. And we're gonna put on the unit circle. And let's add 3 points, A, B, and C. Okay, so here's a question. What's the reflection of C across AB in terms of the complex numbers A, B, and C? And for this to work, we note that we don't need C to lie in the unit circle. So the formula for this is if the complex number corresponding to point A is A, and so on, then the formula for C prime is that complex number is A plus B minus AB C prime. Again, this is good to prove, but so do that on your own time. All right, and so what if C lies on the unit circle, which it does in this example? Then this actually equals A plus B minus AB over C. Why? Because the conjugate of C actually equals 1 over C when C lies on the unit circle. And this is a nice property of the unit circle. And this is true because C times its conjugate equals 1. Because if C is, for example, x plus yi, and then C conjugate is x minus yi, and the product of these is x squared plus y squared, and that's equal to 1 since it lies on the unit circle. So that's the formula for reflecting something. Note that A and B must lie on the unit circle for this to work. Okay, and so now let's find the altitude from C to AB, which is here. So this is easy because it's just the midpoint of C prime. And so C prime is equal to A plus B minus AB C conjugate. And C is equal to C. So this point in the middle, let's call that C double prime. So C double prime is the average of these, which is 1/2 times A plus B plus C minus AB C conjugate. And we can replace that C conjugate with 1 over C if C on the unit circle, if necessary. C lies on the unit circle. Okay, so that's how to find reflections, and yeah. So now let's do an example problem, which should illustrate the power of complex numbers. Okay, so let's consider a circle, and let's choose 4 points on that circle. So we have a cyclic quadrilateral ABCD. And so now let's take the triangle BCD and let's find the orthocenter of that. Yeah, and this is an example problem. So the orthocenter of this triangle is around here. And let's call that point HA. And then we have one line. So we've drawn one line AHA. And we can similarly define HB, HC, and HD by taking orthocenters of those triangles. And we want to prove that these 4 lines are all concurrent. So it turns out this is not that bad using complex numbers. So as expected, let's put this on the unit circle. So it seems like ABCD is a good, the quadrilateral ABCD is a good choice in quadrilateral to inscribe in the unit circle, because, well, what else would we set as the unit circle? This is a classic choice. When we have like a cyclic quadrilateral, inscribe it in the unit circle. And this is almost certainly the most popular. All right, so let's find the coordinates of HA. So let's find, not the coordinates, the complex number there. So we know this. And so the orthocenter of BCD, which is HA, so we know that BCD, that's a triangle that's inscribed in the unit circle. So its orthocenter, HA, should just be B plus C plus D. All right, that was easy. Similarly, HB is A plus C plus D, and HC equals A plus B plus D, and HD equals A plus B plus C. So we want to prove that AHA, BHB, CHC, and DHD, those are concurrent. So they meet at a point. So we could go through and like bash out the equations of those lines, but it turns out that there actually is a formula for finding the intersection of 2 lines, and that was the intersection of 2 lines, and we could do that for the pairs of lines and then prove that they're all the same point, but there's actually a much better solution. So let's look at the midpoint of AHA. The midpoint of AHA is going to be the average of A and HA, which is A plus B plus C plus D over 2. And let's call the midpoint of AHA to be M of AHA for some function M, which is the midpoint. Similarly, the midpoint of BHB is also going to be A plus B plus C plus D over 2. And so on. So the midpoints of all these lines are the same. Midpoints of these lines are the same. So that means they're concurrent because they all meet at, and we proved the stronger statement that they all bisect each other. Because if all the midpoints are the same, then they meet at that point A plus B plus C plus D over 2. All right, so this was a quick example. And that will be the end of this first video in the series of complex numbers, in the series of bashing geo with complex numbers. I hope this was a good introduction to this, and if you're watching this video right after it was created, there currently is no second video in the series, but if you're watching this a while from when this video is created, there will be. So keep an eye out for that, and I hope you start bashing some geometry with complex numbers because it's a very powerful tool. Thanks. Please like and subscribe if you like this video. Bye.